I think we're going to go back to our favorite intersection.
So while we're waiting for that, I'm curious, how many of you know what is IS-95? Can you raise your hand? Higher. Nobody else. And Ray. 4 people. Okay, so IS-95 was the second generation cellular standard. So in 94, that was the big thing. It's a CDMA standard. But frankly speaking, that's what brought us here. And part of my motivation for what I work on stems from what I worked on in 93, which was implementing one of the first ASICs for the CDMA standard, the IS-95 standard. And the story goes like this. So that standard, it was a competing standard to, that was a CDMA standard. There was a TDMA standard also in the United States, and there was GSM in Europe. So one of the big things for CDMA standard was that it's interference based. So essentially interference limited. So the way it worked is that every 10 milliseconds, a base station would send a command signal to every single mobile and for the power control. So, and every 1 millisecond, you will get the power control request. And mobile had to respond to it within 1.5 milliseconds. So that's what they call real time. So I was coding part of that stuff in what I was doing. So anyway, that haunts me to the day today, except that now rather than talking about, and that power control bit was literally one control bit. So if you got that control bit, you had to up your power for 1 dB or go 1 dB. So anyway, 1 millisecond, 1 dB. So this is a little bit different now. I do ask my students, and they don't always enjoy it, to worry about latencies. So latencies are a problem, and I'm not sure that enough many people know what real problem latencies are. So this is my favorite traffic intersection, the Cosmos testbed. The first pilot deployment is, you'll see in a couple of seconds the image of that. But the goal of Cosmos is to provide ultra high bandwidth, very low latency communications and associated with edge computing, sort of high-end GPU-based AI type of edge computing. And at the time when WinLab and Columbia were building all of that equipment, I joined Columbia, or a little bit later, and then I started, wherever they would put a node, I would climb on a ladder and I would put a camera. So that was not funded by Cosmos, but anyway, I did it. So now that's interesting. It became interesting. And so what you see here, do you have a laser pointer or not? The big button, okay. So this is 120th Street, this is Broadway, this is Amsterdam Avenue, and this the Hudson. So this is south and this is north. And this is the engineering building, Mud Engineering Building in Columbia. So this is our traffic intersection. Anyway, what we have deployed there, anyway, another look at the same thing, Amsterdam Avenue, Broadway. And these are my 4 cameras. So I either climbed literally whatever, it was 20 meters above the pavement. So they put me on this thing that goes up and they put the camera and even, you know, whatever he does with the camera. And then the 12th floor was different. It's like you can fall out of the window to put these cameras on at Columbia. But we have had these cameras for now 7 or 8 years and collecting lots of videos and trying to, you know, take advantage of the AI and deep learning is happening. You know, we deploy whatever people have off the shelf, and then we figure out why it doesn't work. And so I'm really a radio guy, but I haven't been doing radio in the last 7 or 8 years. It's all about applications. High bandwidth type of application, is that right? I mean, when you do video, you know, the compression rates that they have is you know, 50 times or whatever. But for 1080p, it's maybe 12.5 megabits per second. So I guess I'm sort of comparing this 12.5 megabits per second to that 1 bit that Qualcomm had or we had for IS-95 standard. Can I close some loop very fast such that even if I have 12.5 megabits per second video, can I do something useful with it and provide feedback to the participants who are in the traffic? So that's where this talk is about. These are the 4 cameras that I've shown you. So this is from this is 120th Street. Anyway, you look at the same scene from the same cameras. The other thing that I like to think about is diversity. Is that right? In radio, everybody worries about that's a great thing. we still haven't done the proper way of using diversity in videos, actually. You know, you could do it at all sorts of levels, at the pixel level, at the pause detection level, and so on. So that's another thing that some of my students are working on. So these are the research topics. Clearly, students want to do something with LLMs, so we do something with LLMs as well. But it's about, let's say, anomaly detection in you know, people who are driving in these intersections. They may be going at whatever, 10 kilometers per hour, 20 kilometers per hour. It turns out that you'll see that it's actually a challenge if you try to observe and react in whatever is real time. That's not easy. So that's what I'm talking about here. The applications, so Cosmos was really the thing that made another thing happen. It's an engineering research center that Jorge was referring to at Columbia. So that's what ERC uses as the basic thing. A bunch of different application focus areas. And my thing is these smart intersections. So today, I would argue, if you that particular intersection, it's a busy intersection, but not as busy as Times Square. I think that if you put, let's say, 12 Teslas right now, autonomous cars, and have those 27 pedestrians in the streets, nobody's going to move. Regardless of the fact that what they say about autonomous cars, they're just not going to move. So the thought is, can the infrastructure help with it? And one way that infrastructure could help with it, if we have these cameras and we're observing what's happening, can we do something useful, detect, track? Can we harvest data from these autonomous cars? Maybe their videos, or maybe some metadata from their videos. Can we push that through the telecommunications infrastructure into servers that are either here at WinLab or at Columbia, do some inferencing, do some higher level reasoning, and provide feedback in real time to these users. So now I'll talk a little bit about physics, because again, people don't realize that it's actually pretty tough. So we have to support very low latency. We have to have sort of high-end edge cloud computing, and you know, you run all of these machine learning AI. It sort of turns out that the speed at which you can execute these object detection tracking algorithms is pretty fast. That's not the limiting factor in terms of actually doing the inferencing on videos. That happens very fast. The bigger problem is really the communications piece. So from the sensor, which is a camera, pushing it through the network, the way it works right now, and the inferencing is not the problem. So maybe what could be an application? So I'm not going to run the video here, but the application could be like this. So I have a camera, the video is running, I'm detecting all of the objects, and I'm tracking them, and I want to broadcast a map, this map that I'm observing, to everybody who's in intersection in real time. So you see, so everybody who's in intersection, every Tesla sees everybody else around the corner. Is that right? Whatever that means, use it somehow. So what would have to happen in our network for that to be able to happen? So I call that a radar met, by the way, and I'll keep talking about real time, but let me remind you a little bit of physics. So I guess I come from Europe, so kilometers are my thing, and let's think about the slow moving vehicles, 10 kilometers per hour. That turns out to be 3 meters per second. So if I really want to be useful, I would like to tell Tesla not to kill anybody within the next, what is the movement? Well, 3 meters is too far. It turns out that you move in 1 second, you move 3 meters. So if my feedback comes 1 second later, Tesla is going to hit somebody. Is that right? So I'd like to do something faster, maybe. So making some sort of a target and completely making this up myself. So the number that I like to think of is 30, because very frequently the video is taken at 30 frames per second. So I'm just going to divide 1 second by 30. And I'm going to get to the number of 33.3 milliseconds. And if I divide 1 second by 30 and I convert that into meters, that's going to be 10 centimeters. So I said, okay, if I'm able to close the loop within 33.3 milliseconds, and then maybe Tesla on its own can press the pedal brake and say, I stopped, I'm not going to kill anybody. So I made it up. So now we have a target. Can we close the loop from camera taking these images, pushing that information through the network, doing some inferencing, composing this map and sharing that map, and whatever, the Tesla actually does some action. That's my target. It's not easy. I mean, even for the first principle, I don't know if it's first principles, but if you've done any video coding, you know that there is this notion of I frames and B frames and so on. And when you buy a camera from off-the-shelf camera, you have no insight into what are the buffers. So we have all of these cameras that have a security cameras from some vendor. Is that right? I don't know what their buffers are. They don't tell me what their buffer. I don't know what is the delay. The other problem I have, I cannot synchronize them with NTP or PTP timing, network timing. So I actually cannot timestamp the frame so that they can even measure what is my delay and latency. So I would like to timestamp that frame. I would like to stamp with exactly the same synchronous timing with the server here in WinLab and measure. I can't. So now I'm back to my 1993 when I was actually building that chip and writing the code, and my students are now going to do it rather than using off-the-shelf NVIDIA software stack or whatever. We're just going to do our own thing, but we're still not there. So that's my target. So I'll give you a little bit, a couple of more numbers, just to sort of an indicator. We've done some measurements, and it's always like, okay, let's do the next measurement. What's the delay? If you buy a camera, which is some USB cameras, what could be the delays? Or if you do inferences, what are the inferences? You know, one of the biggest challenges we have is when Ivan tries to deploy this network through the Columbia infrastructure, they don't give him ownership of the routers so that he can deploy NTP or PTP. So that's like a practical problem. But you can imagine that if you have a video-based system, you sort of break it down. I capture the image, I do image encoding, I transmit. I mean, so this sort of skips the fact that the streaming is with the RTP, RTSP protocols. And that's also something that you really don't have control over how much timing you lose that. So one could be motivated to think, oh, can I come up with some specialized new, simplified metadata, video encoding type of stuff to minimize the delays? And can I replace RTP, RTSP with some customized transmission? It could be even raw data transmission, just strictly focused on, I just really, really want to have low latencies because I'm struggling with latencies. Anyway, so these are pieces where you have these delays accumulating, object tracking, trajectory forecasting. You know, how do you share data? What does broadcasting mean? Do you use some known protocols like MQTT or people who are active in 3GPP, you know, haven't been active in standards for a long time. But what is the dedicated channel that I, as an application developer, can have full control over to have minimal latency to communicate over the cellular system? I don't know. I'd like to know that. You know, maybe more Oren guys may be able to tell me. This is just another view of the same thing, except that somehow from the views of the UDP rather than TCP. But you know, all sorts of conversions, video, parsing, packets, streaming, and so we do measure all of that. But it's tricky. And a couple of measurements. This is the simplest or the lowest end. I think they're not going to produce it anymore. The so-called NVIDIA Jetson Nano tiny devices. They're not so tiny. In NVIDIA, when NVIDIA says low power, it's like 30 watts. It's not really low power. Is that right? But doesn't matter. It is the lowest power device that we do a lot of stuff with it. So there is really no problem. These are all of these inference-based deep learning methods. All of them are doing just fine. We run fast enough that we don't have a problem with real time doing the inferencing. So our problem is more in sending the data. Another, you know, the latencies in video coding, yeah, we immediately start seeing the numbers that bother us. You know, whatever we measure, this is too much, 20 milliseconds. If just in video encoding gives me this latency, I'm completely in trouble with my 33.3 milliseconds. So this is, these are a little bit, the other one were lower resolution, they're higher resolution. So again, these are the numbers that we measure and they're just way too high. So something else that has to be done customized to be able to do somewhere in the future some sort of video-based application that you can harvest, do inferencing on, and provide a real-time response to. I mean, if you look strictly at like TCP or UDP, some little detail, that all appears to be fine and fast enough. But when you compose everything together, then it's when it starts falling apart. So these numbers are small, but when you start composing everything together, they get us into trouble. So as a summary, I keep thinking that first, video. Why video? Whenever you can, you should send metadata. So if you're talking about harvesting the data from vehicles, they shouldn't send us videos, is that right? They should send metadata. They should locally do something that's useful for us, for the whole community. We should harvest that and process it. When we do video, I mean, there is a whole discussion that the whole community has. What is edge computing? Do I put my whole computing stack as much as possible right next to the camera? Well, the problem is still a 30-watt device. So this NVIDIA Jetson is still a 30-watt device. It's still really not low power. Or do I say I just put it into the network, transmit it, and send it whatever to the edge server, which is maybe 300 meters away or something similar. So that's still not sure. We're not sure what to do. But it's quite substantially so. Are there dedicated super low latency channels that applications could get hold of? And I mean, in these 3GPP standards and above or whatever beyond, are there ways of applications to capture and be able to deal with super low latencies? I don't know. The operator does that at a very low level, but I'm not sure that the application has it. So that's all I wanted to tell you. In a way, potentially futuristic applications, but in my head, it's like 1993 was 1 millisecond. I'm still there, 30 milliseconds, just a little bit faster. So that's all I wanted to tell you. Thank you.
Questions?
Thank you. It has been a wake-up call. Yeah, it's interesting when we slow down and think about the latencies that we need to fulfill, to meet.
So it's interesting. Different communities have different understanding of latency. So very frequently I hear from people, oh, no big deal, 1 millisecond is so simple. But it's actually hard. I mean, this very concrete example is hard.
Yeah, indeed. And also something that more than a question is a comment related to this. It's the understanding of deterministic performance. We take things for granted when we connect things, and our networks are not deterministic. There's a big research area on deterministic networks, but I think that even with the latest developments in this area, we are not capable to still meet these latencies.
Yeah, I don't think we are. That's the best, to the degree that I understand it, we are not able to do that. But it's maybe a target. What should happen or which direction to go in. I remember maybe 10 or 12 years ago, you may have heard of the term called tactile internet.
Oh yeah.
So the goal was 1 millisecond. That was sort of to be baked into the 5G standard. But what he forgot about is that the speed of light is 3 times 10 to the 8 meters per second. Multiply that with 1. I mean, the idea is I can do gaming between China and the United States at 1 millisecond. Well, no, because you multiply 3 times 10 to the 8 with 1 millisecond, that's 300 kilometers. So there is never going to be a tactile internet where you're going to game in China and the United States. So it's like you always have to ask a little bit about physics, or what is actually doable. What's fascinating, many people you do ping, and it's like, oh, ping, whatever, this server, it's only 3 milliseconds. So everything, fine, it's super fast. That's not true. You just pinged. It's a tiny little thing that pinged the network. When you actually want to do real applications, it doesn't happen so fast.
And I guess when you're doing video conferencing and things, right? There's buffering going on that's somehow helping you with all of the non-deterministic latency that's in there. Yeah.
Absolutely. So to us, it appears real time, but you have about half a second delay that you're sort of not really perceiving.
Even if you look at the MPEG, right? Typically, it's at least 10 frames before you can actually get the outputs out. The latency is actually not 33 milliseconds. It's 10 times 33 milliseconds, just to get the first packet out, right? So therefore, if you have an MPEG camera, as we've observed over and over, you are way beyond the 33 milliseconds. You're at already hundreds of milliseconds, not because of physics of transmission or anything, but just because of the how the off-the-shelf cameras behave. Now, of course, we are talking about doing something fancy with the raw, what we would call the raw cameras, but that's also not easy. I mean, if you look at the frame size, right? I mean, suddenly you are talking about, you know, at least few packets in the network to just get the frame from point A to point B. And even that, if you have protocol that needs to cover the you know, loss, if it's a wireless link, can cause additional delays. So, you know, things are not easy. And of course, everybody wants a higher resolution frames and all that stuff. So
I guess you don't really want a video camera, right? You want a video sensor somehow. Right?
yes. So ideally, if camera can give you objects, metadata, embedded, doing everything with 1 millisecond, we would be very happy, but that doesn't exist.
So that's discussion about low power end device that is going to give you this metadata. Where do you put it? And do you have the power supply for it?
And then we make it even worse with LiDARs and these sources. You know, if LiDAR, I think, is about 200 megabits per second feeding stuff in. So that gets even more complicated.
Okay, but one thing I have a quibble over, so your radar challenge, right, was about providing information around the corner. I don't think this is working anymore.
No, maybe we are quiet. I don't know.
But then your latency requirement, is related to a car running into a person directly in front of the car. So maybe your latency requirement is too rigorous for this radar application.
Yeah, let's do that at 50 miles an hour, and then let's see how far, what is the braking distance and all that. So, you know, it gets much worse.
On Friday, I talked to the guy who is a robot guy in Nokia Bell Labs. And he reminded me of stuff that I knew in the past, but for their robots, he says, it's hopeless. What we do, we have an embedded device. That thing runs within 1 millisecond, has nothing to do. There is no OS, there is nothing. Then he has ROS operating system that runs in tens of milliseconds per second. And then he says, we don't even try to push to the network anything that's faster than 300, 400 milliseconds. So that's the reality of these guys who really deal with, you know, robots. I don't know. So maybe this is fantasy. I don't know. But if you wanted to interact with, then you would have to try to do this.
So there are some people that are working on. Is someone else talking?
Then.
Oh, online. Okay, Merab. Sorry.
Yes. Yeah. I just wanted to chip in here. So really interesting presentation, but I just wanted to I don't know, guide the conversation towards Zoran as well, where I'm seeing a lot of AI applications where people use large models, they use large language models to try to make predictions for different control applications where the inference time is just crazy long, where they're trying to do, I don't know, predictions or even control something with a model that, I don't know, it takes longer to predict and then you're basically trying to control in the past. So I'm not really seeing a lot of papers where people actually measure how much time it takes to do the inference. And then those models might even work with if there's one user connected and if you're trying to make a prediction for one car. But if you try to do it for a very busy intersection, it would be almost impossible to run models like that.
I completely agree with you. I also think that the CNN, convolutional neural networks models, are good enough for whatever we'll need for object detection and tracking. So it's interesting to read the LLM with transformer-based models for that, but I don't think it's necessary. And CNNs are fast enough and good enough. But that's a commentary on the image type of stuff.
Yes, but once that extends to other control applications in the network where the constraints are even more strict, it becomes an even bigger issue. Like even thinking about the AI applications, not even can we do that, but can we do it fast enough?
Yeah.
So I just want to add to that that's why if you look at the Accord and others, nobody's talking about X apps. Everybody's talking maybe about R apps, and X apps are sort of pushed a little bit to the side because there are all sorts of issues of how do you really do this in a deterministic way, and you know, we are talking about tight controls in the fairly sensitive type of environment, right? I mean, I don't want to think about what happens if your say power control loop is a little bit late and then the whole network collapses because things start floating.
Yeah,
Yeah.
good point.
That's exactly